Hey everyone, great crowd today. First of all, thanks everybody for coming. I'm coming from Seattle, and great to be here in the Bay Area to visit my sister, and conference is a good excuse. My name is Vikrant. I am a senior staff engineer at SoFi. SoFi is a fintech, but I'm here because previously I was a senior software engineer at Amazon S3, where I worked on building core distributed systems and also storage software. And from the last 2 years, I've been working in SoFi on the cloud. So my first 8 years I spent building the cloud. The last two years I've been spending time of building apps on the cloud. So that's something about me. So today's topic is dive deep into cold data archiving. We'll go through what cold data is, and we'll go look at some cloud offerings from AWS, Glacier, AWS, Azure, and what they have to offer. And also we'll do a sneak peek into what it means to build an archival service or a storage service at scale. So wherever you are in your cloud journey, I'm hoping that you'll walk away with building your own or either using one of the services on the cloud. Okay, so wait, why am I showing compute growth? Because if you see, there is by 2030, the graph is just going up for the compute. But what does compute work on? It works on data. So that is why this graph. But let's get to the real elephant in the room, which is storage growth. By 2025, it is estimated that world is going to have 125 zettabytes of data. That's a lot of data. So what does it mean to what does a zettabyte mean? If you look at the magnitude, it's 1 quadrillion megabytes, or 55 million LTO9 tapes, or 18 terabyte hard disks, for example. So you can look at the scale or the amount of data that we're going to have by 2025. That's just 1.5 years away or 2 years away. Okay, let's discuss what is cold data. Cold data is, as you know, infrequently accessed, especially things like logs that are not really something that you go look at on a day-to-day basis. But there is some value in holding them for purposes which we'll get to them later. And it's not required real time. Most of the time, cold data is not required real time. They just stay there for other purposes. And it's lower priority. That means they don't have to be active in your databases. And mostly it's older or historical data. A lot of times, for example, you have data from 2017, which you don't really go open on a daily basis, right? So it's mostly older or historical data. And it's estimated that almost today, 60% of data is cold data, and the gap is going to widen to 80% by 2030. Okay, so why do we need cold data? I work in a bank, so I understand we have to keep the transactions for 7 to 10 years for compliance purposes. So banks need it for regulatory compliance. And governments for various legal and audit purposes. Like governments have to deal with litigations, disputes, and all that stuff. So if they have a trace going back to what the data is and why today what it is, then governments would benefit from using that cold data. And this is my favorite area, genomic data. I think there are a lot of revolutionary aspects that are happening. For example, companies like CRISPR, Illumina, they want to look at, for example, what is the evolutionary pathways of humans or any other species, right? They can go look at the colder data to get that information and then find how a certain species have adapted over time, for example. And disaster recovery, shit happens a lot of times, and when you have something that you can go back up and restore from and go back do point-in-time recoveries, then that cold data would really help you, where you can do point-in-time recoveries, and it might be a business ending event which you can recover from. And obviously today it's AI and ML. Last decade was about every company was a data company, but now every company is a AI and ML company, right? So what does a good LLM needs? Again, data. Where do you get that? If you have cold data that you can go churn on and build your LLM. And one interesting quote that most of the times missing or deleted data is most likely the data that you need. So again, where do you get that treasure from? It's cold data, right? Okay, what are some of the benefits of archival? Like we know we spoke about cold data, but we also want to archive them, so obviously. So what are some of the benefits? Obviously cost. Having data stored on, for example, tapes or for archival purposes is cost effective. And scalability is scalability and performance is interesting because, for example, you're dealing with a live database. The live database is doing real-time traffic. Now, keeping your database leaner, having lesser indexes will help you with scalability and performance. But where do you throw the data that is older or that is not needed? You can archive them, right? So colder data again helps with keeping your database leaner. That's structured, of course, but you can always go from structured to unstructured. But that will help with scalability and performance of your systems. And you can see the pyramid that how as hot data, which is the top, is expensive, and as you come down, the data that is colder or frozen is cheaper. And also there is I/O bandwidth latency performance that you can look at. That we'll get into this later. Okay, as promised, what are some of the archival solutions on the cloud that are available today? There is the popular one, which is S3 Glacier. S3 has multiple storage classes. Standard is where a lot of data sits in, and also Glacier is another storage class where you can archive your colder data, and Azure also has Azure Archive Storage. Google has Google Cloud Storage, and Oracle, IBM have their own flavors as well. And most of the systems, they can do two kinds of uploads to your archives. One is a direct upload, and one is something called lifecycle, where initially your data can reside in a hotter storage class, like standard. And then you can set up your policies to move or transition your data to colder storage classes like Glacier if they hit a 30-day mark or a 90-day mark based on what your compliance and requirements are. And you can also build things like AI and ML if you're interested on these, and then transition your data from hotter to colder storage classes. All right, so what are some of the cloud archival benefits? The first one is obviously serverless. You don't have to maintain any infrastructure, and also you can pay as you go. And it's scalable and elastic. This is one interesting one as well, where you can scale up and down, in the sense that if you think you don't want your storage to hit, let's say, 1 petabyte, you can set up policies to delete your data, so you can always be in that range. And elastic in the sense, again, it ties back to serverless. You can scale up and down. You don't have to worry about servers and scaling up and down. Someone else is going to deal with that for you. And my most favorite one is native cloud integrations. So a lot of times when you have this data, what do you do with this data, right? You get the data, but you'll have to transform it, convert it, and dispatch it somewhere, right? So these native cloud integrations will help you with building that ecosystem of things, and not have to worry about just storing the data in one place. But these integrations will help you transform it and convert and send it to your customers, for example. As I said, lifecycle, you can set up policies in the cloud, so you can move data between your colder and hotter storage classes, and vice versa, based on for example, dates or even AI/ML. Security. One other thing is you don't have to. I mean, a lot of times these, or almost all the cloud providers, they provide you with encryption at rest. Where you can bring in your own keys, or you can use keys from their own providers. And also, they can also provide you with access controls. For example, you can set up things like, hey, I want to give access to this account, for example, or this website, that they can go download these objects. And obviously, there is encryption in transit as well with HTTPS and stuff. And cloud providers also provide you with SLAs for durability and availability. For example, S3 provides you with 11 nines of durability and 4 nines of availability. So this is something that they provide and hold high standards for. And some second order benefits is you don't have to maintain a data center where you have to think about host, procuring host, racks, and also maintaining temperatures, especially for example, if you're doing archival, you'll have to run your tapes on at a certain temperature and humidity levels. And this is becoming a big one, which is carbon footprint. Now, because you're storing these things, now you also think about how do you maintain your carbon footprint, because this is something the regulators are coming after very quickly. So that is something that you have to worry about, but or the cloud providers have to worry about. And as I said, capacity management, you don't have to procure your host racks, you don't have to look at what's happening, and you don't have to do capacity planning and stuff, etc. And with cloud, you don't have to have an operational team that is constantly looking and working on hardware or replacing hardware, etc., etc. And the interesting one is distributed systems are hard. You don't have to solve those problems all by yourselves. You have all the best people on the cloud solving that for you. And storage media advancements, again, if you're not in the business of storage, there are a lot of advancements that happening. There's DNS storage, there is hard disks that are getting cheaper and also denser. You don't have to worry about all those things. You can build what can be helpful for your company and your customers. So let's take an example of S3 scale. This is something that S3 team put out in a website called All Things Distributed. So check out that, it's really interesting. So today S3 holds like 280 trillion objects, and it's dealing with over 100 million requests per second. That's quite a large scale of data that you have to, that S3 or any cloud providers can support and deal with. In fact, when I was driving, I was thinking what it means to be a 280 trillion. So I asked ChatGPT, hey, can you give me something comparable to 280 trillion? And it said 280 trillion is equal to number of trees that are on planet Earth, and 280 trillion is equal to number of cells in your body. So that's quite amazing scale that S3 or any other storage provider deals with. And again, it's not just S3, it can be any cloud provider. They have events, like when you do a put or a get, you can send these events. So for example, S3 every day sends 125 billion events, and there is also replication, like because cloud providers also help you with disaster recovery. They have like many regions across the globe, and you can always, like when you put an object to one region, they replicate it to other region, and that itself is 100 petabytes per week if you look at S3 scale. And for cloud storage retrieval, there is 1 petabyte that is moving across Glacier and S3 storage classes, which we spoke about. And the interesting one is 4 billion checksum computations per second. These are massive numbers if you think about it. Like at that scale, operating at that scale is really hard, and this number is mind-boggling. And obviously there are other things, but you can take a look at it. So let's look at some of the access patterns of these. So lower cost storage is slower because they are mostly on tapes, and reads and writes are async. Let's see what that means. So there are two ways to get data into your archival or cloud archival, right? One is a direct put to archival storage, or one is a life cycle where data first stays in a hotter storage class, maybe they're in SSDs or hard disks, and then after some time, let's say 30 days, they're automatically transitioned to colder storage classes. So that's how writes work. But what does it mean to stage your data? So when you're dealing with a direct upload to a colder storage class, you cannot really do that because tapes, for example, cannot. They're not good at random access. They are sequential access, right? And they are slower. So the cloud providers are internally are leaking an abstraction that they are going to write it to a faster storage service or a disk, like a hard disk or SSD, and then stage your writes, and then build asynchronous systems that are taking these writes and taking these writes from the faster storage media to a slower storage media. And they're making it seem like you're actually writing to a storage or a slower storage device, but it's not. And when you want to read this data from archival, now you are exposed, or there is an abstraction leak, for example, where they have to move this data from the colder storage class to a hotter storage class. So you need to do a restore first. As a customer, as a client, you need to say, I need this data, and you need to do a restore. And based on how much you're willing to pay and how much you're willing to wait, there are a few tiers, maybe like 3, 6, 12 hours, where your data would be moved from like older or a cheaper storage class like tape to a faster storage class. And with that, one good pattern that everybody, or something that customers have to follow, or something that you can follow as well, is to prefer larger objects when you're archiving. Because with larger objects, you don't have to do many restores. You can do a single restore and get your data back. And also, cloud providers do provide you with events after completion. So when your data is ready after a restore, you can use those events for your advantage, and then do computations, and then fan out this to your, let's say, message queues or your customers back. Okay, so let's go through what a native cloud integration looks like. So just an example to get a feel of what we have spoken so far. So let's say you're a client, or let's say that you're a company. That company is taking dog pictures, cute dog pictures, and providing a website on top of it. So you can, let's say, pick a dog picture that is very popular and then upload it to, for example, your file store. The file store can be S3 or Azure Cloud Storage. So let's say the cute puppy is very popular right now, and so when you're uploading to your file store, you want to be highly secure, right? You want it to be, you want to make sure it's encrypted, and it's not stored. You're not storing plain text, for example, in your file store. So you can bring in your own key, or you can use a key management service provided by cloud, because every cloud has a key management service, and you can maybe use a symmetric key, or you can use envelope encryption or any other new fancy encryption types, and then encrypt your bytes in file store. Now you can also set lifecycle policies. So when it's hot, when the puppy is hot, you can also use cloud CDNs out of box. Like Amazon has CloudFront. You can you don't have to go to cloud. You don't have to go to file store every time. You can fetch it from the CDN, which are across the globe again. So that is something that you can get with the cloud integration for free. Not for free, you have to pay, but still, that is something, there's no setup overhead. And also you can set up policies that, hey, after 30 days, I want to migrate my data migrate my puppy from a file storage to an archival storage class like Glacier, for example. Now, the egress part is interesting. Now, the same company, let's say, wants to send out memes to its customers. So let's say the puppy that is in archival became popular again. Let's say Elon Musk did something and they want to bring that puppy back. So client, excuse me, or the customer can send a restore request to the file store, and the file store will do a get on the archive, and then cloud providers will take that from the archive and put it into a faster storage class like standard. And once the data is available, they're going to send a notification. Now, the notification can be consumed by like different native services. Like, let's say there is a notification hub or SQS, for example, in Amazon, that can pick up the data. It's a message queue, and then let's say listening to the some notifications, and once it gets a notification, it can then send that notification to, let's say, a serverless system like Lambda, which is a compute. And that compute can maybe do customize puppy pictures, customize the same puppy picture by customer, and then fan out. Now, the serverless system can also get, because there's encrypted bytes, can get data from your key management service, decrypt it, and then transform it, and then fan out to multiple customers or your customers. So you can build differentiated use cases and quickly using these cloud native integrations with the data that you have in archival and also file stores. So this is one big benefit with using cloud, which is the cloud native integrations. All right, so let's switch some gears. We have spoken about cold data, we have spoken about cloud and how cloud providers work and how to set up these cloud native integrations. Now let's see how to build a system like this. If you were to build a system like this, how do you do it? That too at a certain scale. So obviously you want to build an enterprise grade system. It's something that your enterprise can be supported, and obviously you have to deal with multiple storage devices and multiple hosts. So it's not going to be a single system, single host that is running this. So that means you have to build a distributed system that can be on the storage side, that can be on the metadata side of the thing. Okay, so let's build a conceptual model first. So if you think of a single system, Unix system, what you have is you have inodes, and your inodes point to some offsets on your disk. So if you take the same conceptual model but apply it to how you build enterprise grade system. So you have a key value store. The key value store has, let's say, keys. That's how you're presenting it. And you have pointers to, let's say we are building heterogeneous storage media or heterogeneous storage with archival, and let's say we are building archival with tapes and one with a faster storage devices, let's say SSDs or hard disks. So let's say this is the base conceptual model, and let's build on this. So we're going to build a distributed system, so that means we need to think about how do you replicate the data, because you cannot store it in a single storage device or storage media, so you have to think about your replication strategies. And you also think about how do you horizontally scale your storage media. And heat management is something interesting. So heat management means not temperature, but when you get requests, how do you shard, or how do you encode your data so that way you can do lesser I/O and also and get your data back. And a lot of times we forget about metadata store as well, because when you build a storage media, you also need some kind of metadata store, where just like an inode table, as I said, in Unix. But metadata store needs to be scalable as well, right? Now you can choose, for example, you can choose something like DynamoDB or Cassandra, but if you're using an abstraction, why not use abstraction for storage as well, like using cloud? But again, let's not get there, but you also need to build your own metadata store, and you also need to think about how do you replicate and also scale your metadata store. So that is something that you have to think about. All right, so for replication, obviously you have a Azure coding. Now you can choose your encoding type based on your workload, if it's a bursty or whether it's neatly balanced. But again, it depends on the strategy, or the encoding depends on how your workload is. And a lot of times you cannot just guess it. There are a lot of variables that are going around. So you need to be more data driven. You need to be work what your customer needs or what your needs are for accessing this data, and based on that you need to set up and think about your encoding type or Azure coding. And you need to think about horizontally scaling. As I said, heat management plays an interesting role, and it's based on your workloads like bursty or balanced. And you have to build your control plane as well, because whatever the storage media is, you're gonna replace the devices. You're gonna have to deal with network outages or power outages, and you have to constantly be repairing. So you'll have to build your own control plane to repair the storage media and keep them available. And also you need to think about zones and cells to reduce blast radius, because if you have everything in a single zone or a cell, and if it goes down, you're going to brown out, or you're going to take out your data center or take out your service. So having zones and cells will protect you from that. And in fact, when you use the Azure coding, make sure you shard them across multiple zones and cells, so that even if one of the zone or one of the cell is down, you can still be able to service your customers or your internal customers. And metadata store is also interesting. It's a database. Think about it as a key value store, but the key value store is something that you have to replicate as well. Now that means you'll have to think about algorithms like Paxos and Raft and make that replication strategy. You really don't want to use Azure coding for smaller objects. And consistency will be driven, like if your system is eventually consistent or strongly consistent, these are something that your metadata store derives. Again, you can use something off the shelf like DynamoDB that can give you strong consistency, or you can build your own based on your needs. But again, if you have stringent requirements about not storing any data on the cloud, then you'll have to build this all yourself. Same thing with replication. You'll have to replicate your metadata store using strategies that I mentioned above. And you need to think about your cache. Obviously, when you have like a hot partition and hot object, you don't want to go hit your database every time. You can build caches around it. And ordering, you also need to deal with sequencing and ordering of your writes, so that way it's always the data is written in an order, because your metadata store drives where your pointers are to your storage. Same thing, just like how we discussed about storage media, you also need to scale your metadata store. Like you will have hot partitions when you have systems that are browned out because you have hot partitions. You need to have some kind of control plane that is migrating away partitions from these hosts to hosts that are not taking a lot of traffic. So you need to have control planes and be continuously replicating in the background, so to keep the consistency. And same like metadata, so you need to have your cells and zones, so that you can, even if one of your cell goes down, you have other cells that you can serve these requests from. Some of the problems to consider when you're building is durability. Obviously, durability is the heart of any storage system. So first thing to note is, don't trust any hardware, don't trust any network, and don't trust any system that you're building. Always have checksums. Make sure you are doing checksums continuously, even for in-memory. And both for your metadata store and your storage media, have continuous repairs, because disks will die, there is power outages. So make sure you're continuously repairing these and exercising those areas. And availability, obviously that's another SLA that you want to provide to your customers. Think about blast radius. As I said, make sure you have cells and zones that you divide against, and also have things like storage device availability. Have some health checks continuously running for you. So if your health check fails, then you can bring in your repair service and repair or migrate data. So the last one is, I think we spoke about building a system like this, but think about, because we are going to support heterogeneous storage devices, because we are going to support hot data and also cold data, you need to build a lifecycle system as well that is continuously looking at your data and understanding whether it's hot or cold, and then moving data between your hot and cold storage classes based on the data hotness. And you can build a lifecycle system things based on like last updated time. Like if the last maybe this is the last access time. So if you have a last access time of, let's say, 30 days, then that is something that you can take up and then migrate the data bit to a colder storage class and save costs, for example. And obviously you can write a new transition based or you can build your own transition based on AI and ML on that data. For example, if there's data that is getting hotter once every 30 days because there's a regulatory requirement for a company, then you don't want to transition exactly the 30th day, but maybe you can derive some, do some analysis and maybe transition after the analysis is done. So that way you can save some costs. And you have to build your own restores, obviously, because now you're dealing with heterogeneous storage media. You need to move from, like for example, a tape to a hard disk. So when you do that restore, your customers or you can go access it. So these are some of the challenges, at least very high-level challenges. Again, this will amplify when you're building things at scale. But a lot of times, I would say these decisions have to be taken using data. Or experience. It's not going to be easy because there are a lot of variables and parameters involved when you're building a system like this, especially with a lot of things changing around having bursty workloads or balanced workloads. So that is something that I would encourage you to do. Okay, with that we are at the end of the talk. I hope you got something out of it. Let me know if you have any questions. Yes.
So most of those, like you give the example of, the puppy picture and someone tweets and you want to put it straight back to the archive. But most of the archive time to data is around 24 hours to 72 hours, 78 hours. How do you resolve that with certain aspects like that, or time to data being huge comparatively to the need? Like again, a tweet comes up, becomes popular. It's popular for not 3 days, but maybe for a few hours, and you want to react quickly.
Yeah. So the question is, how do you deal with that timeline when you have to transition your data from an archive to a faster storage? So because in today's world, you need data fast, and you can't wait for 12 hours or 30 to 36 hours. That's a good question. So first thing is, you don't want to move that sensitive data if you think that is required quickly. You don't want to move into archives. And there are different tiers. If you're thinking about cloud, the different tiers, like you can restore your data in minutes, you can restore your data in hours. Now, if you pay higher, obviously you can restore it quicker. If you pay lower, you're going to restore it in maybe 12 hours, for example, from Glacier. So the answer is really depends on what kind of data you are trying to archive. And there are different storage classes as well. You don't really need to archive it. You can go to a cheaper storage class where you can say, for example, store in one zone and not in multiple zones. So obviously, if the zone is out, you're not going to have that data at that time, but the chances are low. Yes?
Do you have any concept of data placement together? In other words, if I think I'm going to store this object, I'm also going to restore this other 100,000 objects, right? Do you have any concept of grouping the data for optimized restore, or this is all just a single kind of axis of hotness?
So the question is, do you have a concept of grouping the data? Or data placement. So again, the answer is it really depends, because it depends on the workload. So for example, you're using erasure coding, right? And you use a larger number of hosts when you want to shard your data. Now, if you want to fetch the data, you'll have to go touch many storage devices to do much higher I/O. Like the I/O is much higher. So if your workload, and also it depends also on your storage density. Now, if you can shard it across many hosts or thousands of hosts, for example, then you can easily get that data. That means you don't have to brown out single host, so you can get the data. But again, the problem with that is the tail latencies will be higher. Let's say there is one host during a peak, that one host is getting all the load, then getting that last piece of shard will increase your tail latency for your whole object storage. I hope that answers.
Well, it was slightly different. I think you've answered the question, but more of my question was, can the user control the data placement, right? So in other words, if I'm placing this object, right? So, and I know it goes along with a number of other objects.
Yes.
So whenever I'm going to be retrieving, I'm not just going to be retrieving this one object. I will probably retrieve all 10 or whatever, 100,000, right? So is there a way for me to indicate to the system? I mean, have you thought about this?
So I guess maybe you're asking. So you have so there is something called you can, for example, in S3 you can fetch based on byte offsets. So let's say you have
a question.
Oh, the question is, how do you do data placement? That is a question. So
Did it have something to do with the user?
Yes. Sorry. Can the user control the data placement of the data?
You keep the data.
Yes. Thank you for keeping me honest there. So in S3 you can do something like fetch on your byte ranges, but you cannot really control where your data goes. It's something that controlled by cloud provider and not something that you can control, but you can fetch by byte ranges. For example, if you have 1 terabyte object, or not 1 terabyte, let's say 1 gigabyte of object, and you want to fetch data between, let's say, 100 to 200 offset of that bytes. So you can do that. But the answer is you cannot control where the data goes or how the data is placed. Yes?
What level of granularity does the metadata store have? How can I imagine this if you, for example, have DynamoDB, you mentioned that. Are these just indices and links to files or objects, and how does this cut into the lower level where you shard over multiple zones, for example? I guess there's an underlying file system below that, or does the sharding also go into the metadata system? I have a bit of a problem understanding how the file system and the metadata store work together.
Okay, the question is, how does file system and the metadata store work together? So there are two independent pieces. Like metadata store can be built and scaled horizontally in a different way than the storage media itself. So metadata store, think about it as maybe you can build your own metadata store. Like if you host Cassandra, for example, in your company, or if you use DynamoDB, these databases can hold pointers like, hey, this is the offset for this storage media. Let's say the storage media is of type X and has an ID of Y. You can say that this data is being hosted in storage media Y with offset of 100, for example, and you can do that on your erasure codec data. Like you can add, let's say you do a erasure coding of 5:3, right? So you can add all your 5 hosts with the offset and say this is where you have to go fetch the data from. So that pointer is exactly where that data is in your hard disk.
All goes into the metadata.
All goes in the metadata store, exactly.
Thank you.
Yeah. Yes.
Kind of related. Is there some way, because also certain policy track, right, how long you archive, and then the retrieval time sometimes say the data has to be retrieved back within 48 hours. Right?
Yeah.
How do you handle, in terms of different data has different time that you have to come up with, be able to restore that?
So the question is, how do you handle restore, especially in a time-sensitive environment? So again, it's how much you're willing to pay and how much you're willing to wait. So there are different storage classes, different tiers. Now, if you go use the cheapest tier, you're going to wait for 12 hours. If you go use you have to pay more. A different storage class, even though it's still archival, you can get it in minutes as well. So if you're willing to pay more, you can get it faster. So that's how the pay-as-you-go model is.
So a small question on that.
Yes.
The pay-as-you-go is based on your initial plan or on your retrieval cost? Like it's, okay, I want this faster, then you pay more at the end, like saying, I want this faster, or do you say, okay, I want to store this in a tier that I can access in 12 minutes?
So, so there are 2 ways to do it. I think that's a really good question. There are 2 ways to do it. You have few different storage classes, and based on that, your pay also goes down. If you choose the lowest tier, now the lowest tier is 12 hours or 6 hours if you can pay more, and then there is other tier which can get you in minutes. So if you can choose that tier, you're going to pay more upfront, obviously, but your restore cost will also be cheaper. All right. Thanks for coming in today. I hope you guys have a great time.